Thank you very much, Luke, and good morning, everyone. My name is Nicolas Bellouin, and I work at the University of Reading. This morning, I'm going to talk about a piece of code I wrote 10 years ago, which is called RADAER. And RADAER is an acronym. It stands for Radiation Aerosol, and it does aerosol radiation interactions. I'm not the one to put too much effort in acronyms. So this morning I'm going to talk about aerosol radiation interactions. So first, a little introduction of why it's important to have them in a model like UKCA. Then a little bit the theory, the physics behind aerosol radiation interaction and misscattering calculations. And finally, a little bit more concrete slides on RADAER itself, how it does aerosol radiation interactions, and what kind of diagnostics it provides. So let's start with an introduction on aerosol radiation interactions. And I always like to look a little bit back at history. And with aerosol radiation interactions, we can go back to about the 15th century to the first mention of what we now call aerosol radiation interaction in a manuscript by Leonardo da Vinci. And he noted there was a big plume of aerosols that he could see, and he noted that the plume was much brighter on the side where the light comes from than on the other side. And the way we understand it now is that particles scatter radiation, and some of it goes back to where it comes from. And if it's thick enough, then it's essentially you scattering radiation back to space. So it took a few centuries for someone to really look at aerosols in detail, and that's John Hyken, is a Scottish scientist who made the first measurements of aerosol, and he discovered this new world of those numerous particles in suspension in the atmosphere. And the physics of aerosol radiation interactions arrived in the early 20th century with Gustav Mie, who essentially took the Maxwell equations of electromagnetism, projected them onto a sphere, and described the resulting radiation field as essentially an infinite sum of multipoles. Let's skip to more recently and to the late 1970s, and this is where we got our first view of global aerosols with an instrument called AVHRR, which provided our first aerosol retrievals from space. So on the climate forcing side of things, the story starts around 1971 with Razul and Schneider, who published a paper in Science. They computed the forcing by aerosols and by CO2 and found that aerosol dominated, which means that there would be a cooling of climate. So they got the CO2 forcing wrong by a factor of 4, but what matters with that paper is essentially it launched the idea that you need to represent aerosol interactions with climate in a climate model. Then in the 1980s, there's a Japanese scientist working in Switzerland, Atsumu Homura, who measured radiation at the surface and found a decreasing trend. So there was less radiation from sunlight reaching the surface. And that's been coined later the global dimming phenomenon. And that's been attributed to aerosols interacting with radiation and then decreasing the amount of radiation reaching the surface. So that's the impact of pollution directly on the energy budget of the planet. So here I got the date wrong. It should read 1991. So that's a paper by Bob Charlson at University of Washington in the US. And he did the first estimates of the relative forcing by sulfate aerosols and found fairly large numbers, about 1 watt lost to the climate system because of sulfate pollution. So again, they were wrong by a factor of 4. Our best estimate now of that forcing is about a quarter of that. But again, it was a reminder that aerosols are an important contributor to the energy budget. The latest best estimate of aerosol radiation interaction, so the effective relative forcing of aerosol radiation interaction, is about half a watt, with a fairly large uncertainty bar. So I've said aerosol radiation interaction a lot. It's perhaps time that I say what I mean by that. So essentially I'm talking about 4 processes. So aerosols, which are represented here as little gray box, can absorb radiation. So you get radiation in and you get nothing out at that wavelength. Then they can scatter radiation, so that's an elastic process where you change the direction of propagation of your photon, but not its wavelength. So you can scatter outside your field of view or inside it. And finally, aerosols can emit radiation. So here we're talking more in the infrared spectrum. So radiation which essentially depends on the temperature of the aerosol layer. So why we care about aerosol radiation interaction? So I hinted at that already, but essentially aerosols are part of the energy budget of the Earth, and that's what has been called for a long time the direct relative effect. So that means that if you need to represent the energy budget of the Earth or the top of atmosphere relative balance correctly in your model, you need aerosols to do that. Because they absorb and scatter radiations, they affect visibility, so it could be important for airport operations, for example, or anything that depends on atmospheric visibility. A sizable fraction of aerosols are of anthropogenic origin, so they are emitted by our human activities, which means that those aerosols represent a relative forcing of climate, so that's the notion of effective relative forcing, and that are estimated by the IPCC report. And finally, they are also a useful way to evaluate aspects of the model. It could be, for example, transport against remote sensing products. So does the model transport the aerosols where they should be? So to give you a little idea of the complexity of aerosol interactions, here is an image taken by the MODIS radiometer, so that's a satellite instrument. We are in 2003. This is the Iberian Peninsula, this is the Atlantic Ocean, and this is Portugal. And on that year, there were very strong forest fires in Portugal, and you can see those fires indicated in red, and the plumes of smoke being emitted by those fires. And I want you to look at the plume of smoke, and if you look slightly to the west at an area where the aerosol is not there, and you can see that essentially compared to a dark surface like the ocean, aerosols increase the amount of radiation emitted back to space. So essentially, the fact that those fires are there represent a loss of energy for the climate system. But it's not that simple, because now if you look at the northwest side of the picture, where now the smoke overlies a cloud, and you see that now when the smoke is over the cloud, then the cloud looks darker with the smoke on it than when it has no smoke. And it means that here the aerosol causes a gain of energy in the system. So because you have aerosol above the cloud, you're storing more energy than you used to. So the sign of the impact of aerosols on the relative budget essentially depend on the environment. What do you have below? And it depends on the nature of the aerosol. Do they absorb mostly, or are they mostly scattering? So that's the kind of things we will need to represent well in the model to get the right climate impacts. In terms of numerical weather prediction, aerosols are also important. That's work by Jim Haywood at the Metaphysics back in 2005. And in the Metaphysics model, there used to be a problem with outgoing long-wave radiation, is that the model tended to have what is the sign? Yes, the model tended to have too much outgoing radiation over the Sahara Desert. And that's a problem because it means that you end up with simulating a low pressure area where there should not be, which will impact your forecast over Europe. And this bias in the model has been traced to the lack of mineral dust aerosols. Mineral dust aerosols are quite big, they're quite good at emitting long-wave radiation, and adding mineral dust, the climatology of mineral dust aerosols, meant that that bias was mostly solved. Finally, on the climate side, I mentioned relative forcing. So this is a picture from the latest IPCC assessment reports, as you may have seen it already several times, because that's a good summary of the impact of atmospheric composition on relative forcing. And aerosol radiation interactions are circled there in black. So you see that our best estimate is that aerosols cool the climate, so that's a negative relative forcing that offsets some of the positive relative forcing by long-lived greenhouse gases. And you see also that if you compare the uncertainty ranges, those error bars for aerosol radiation interaction, if you compare those to the error bars on CO2 and methane, you see that we are very uncertain. We're pretty sure that the sign is negative, but it could be as weak as 0, but it could be as strong as -1 watt. So I hope I convinced you that aerosols are important to have in a climate model, and aerosol interactions in particular need to be represented. So how do we do that? Well, we've got a physical theory that comes from Gustav Mie, and it's what I'm going to talk next. But first, I need to introduce a little bit of vocabulary. And an important notion in aerosol science is the notion of size distribution. So the figure here shows the number of particles as a function of their radius. So it's essentially a histogram. You take the particles, you measure their radius, and then you put them in bins and you count, and you get this curve. So those have been measured by aircraft measurements, that's by the Metaphysics aircraft, in different settings. But you see that essentially the size distribution is not constant. There are maxima in that size distribution. And it is possible to find those maximas almost everywhere about at the same place, which means that the size distribution is now described in terms of modes. So a mode is a local maximum in the size distribution. And they've been given name mainly for historical reasons. But essentially you need 3 or perhaps 4 modes to describe a typical size distribution. You need a mode for very small particles, radii less than 50 nanometers, typically called nucleation or Icahn. This is a John Icahn I mentioned earlier mode. So those particles tend to originate from gas to particle conversions. So gases, molecule sticking together to form a particle. Then if you go on a little bit, slightly larger particles, 0.5 microns up to 0.5 microns radius. This is the accumulation mode. So it's named that way because it results from the accumulation of smaller particles that stick together to form larger ones. So the results mainly on coagulation of small particles, but also on combustion processes, which tend to form particles of those sizes. And finally, if you look at the larger sizes, more than 5.5 micron radius, you find the coarse mode. There's often more than one coarse mode. And those particles are, in general, created by friction processes. So think sandstorm, which has been emitted by wind, or a sea spray created by the waves. So that's how to describe our population of aerosol. And the size distribution is really critical for aerosol radiation interaction. The size of the particle really drives its ability to interact with radiation. So misscattering is the scattering mechanism that operates when the particle is about the same size as the wavelength of the radiation. And for most aerosols, that means essentially that they will interact with short wave or sunlight radiation. The larger aerosols can also interact quite well with terrestrial radiation, so in the long wave. So the theory that me got together in 1908 is only valid for homogeneous spheres, but that's actually quite a good approximation to represent typical aerosols in the atmosphere, with perhaps the exception of mineral dust aerosols, so grains of sands, which are anything but spherical. But even that, you can apply correction factors. But we have a theory. We can start computing our aerosol radiation interactions. So what do we compute? So what's the output, if you wish, of the me theory are 3 quantities. The first 2 are the scattering and absorption cross-sections of the aerosol. So they are cross-sections, so they are surfaces in square meter. And if you wish, they represent the cross-section of the aerosol from the point of view of a photon. And the larger the cross-section, the more likely the photon is to be scattered or absorbed. So the key result that Gustav Mie got with his theory is that those cross-sections only depend on 2 parameters. The first one was called the size parameter, which is essentially the ratio between the size of the particle and the wavelength of the radiation. And the second is the complex refractive index, so that's a complex number. I've forgotten I here. So a real part and an imaginary part. And the complex refractive index essentially depends on the composition of the particle and tells you how good it is at scattering or absorbing radiation. So only those 2 parameters and you can compute those scattering and absorption cross-sections. So what do you get, for example? So those are an example of calculation for one particle with a real part of the refractive index of 1.33, so that's of water, and then increasing imaginary part of the refractive index. At the very top, you've got no imaginary part. So that means that the aerosol is purely scattering. And then as you increase the imaginary part, the absorption increases. So what is plotted is the ratio between the scattering cross-section to the geometric cross-section. So if you prefer how the aerosol is seen by a photon to how the aerosol is seen by us. So let's start with the non-absorbing case, so the solid line at the top. And you see first that this ratio depends strongly on the μ parameter. So the size is a strong driver of the scattering efficiency. You see that there is a maximum of scattering around size parameters of around 2 pi, which means that your best efficiency as scattering is when you have about the same size as the wavelength of the radiation. So in this, for the shortwave spectrum for sunlight, it means accumulation mode aerosols are the best scatterers. And then you see after that it decreases, but there are interferences patterns. And eventually the non-absorbing case tends towards a ratio of 2 for the larger size parameters, and that's the ratio predicted by geometric optics. You see that introducing absorption by increasing the imaginary part does two things. First, it smooths those interference patterns a little bit, so you get a much smoother relationship. And also you end up with a ratio of 1 for very strongly absorbing particles for large size parameters. To finish here, important to remember that aerosols are not always dry in the atmosphere. They uptake water depending on the relative humidity, which means that their size increases as water accumulates. So the size parameter will increase with water uptake, and also it's the aerosol's refractive index will tend towards that of water for very hydrated particles. So that's two important things that ME theory allow us to compute, the absorption and scattering cross-sections. One thing that we also need to know is in which direction the photon is scattered. And that's essentially a probabilistic framework. So ME theory allows us to compute what's called the phase function, and it gives us the probability for a photon to be scattered in a given direction, which is computed by the scattering angle between the direction of incidence and the scattered direction. So this is how a typical aerosol phase function looks like. You see that it's very likely for the photon to be scattered forward, but backscattering and side scattering are not zero. And for climate application, it seems also important to remember that forward and backscattering depend on the horizon of the particle. So depending on the solar zenith angle, so the angle of the incoming radiation, part of the forward scattering will in fact be upward and will essentially result in a loss of radiation for the climate system. So most climate models and HADGEM is one do not represent the full phase function in their calculations, although they have the option to do so. But in general, they just simplify the phase function into just one number called the asymmetry parameter. And the asymmetry parameter is essentially measures the asymmetry between forward and backward scattering, because that's really the key information we want to know. So it's a parameter that goes from -1 to 1, -1 for completely backward scattering, 1 for completely forward, and 0 for isotropic symmetric scattering. For most aerosols, the asymmetry parameter is around 0.7 and larger. So forward scattering, it tends to be privileged. So all I've said so far is valid for one single particle, but as we've seen in the atmosphere, we don't have just one particle here and there. We have a population of particles, which is described by a size distribution. So that means that all the quantities that I have defined need to be integrated over the size distribution. So it's really nothing magical. It's just essentially a weighted average of the optical properties weighted by the number of particles at a given size. And you need to do that for the optical properties you require: the scattering cross-section, the absorption cross-section, and the asymmetry parameter. Right. So that was quick sweep of the theory. So really, these are the main elements of it. And now let's see how it's been implemented in RADAER, and hopefully that will explain the presence of some files in UKCA. So RADAER is a bit different to the other UKCA components that you've had talk about and in the coming days, is that RADAER doesn't live within UKCA, it lives in the radiation scheme of the unified model, which is called Socrates. So RADAER takes information from the GLOMAP aerosol scheme within UKCA. So it needs quite a lot of information because a lot of characteristics of the aerosols are required to compute their interactions with radiation. So it requires the aerosol mass in each component, the aerosol number in each mode, the dry and wet diameter, the density of the aerosol, and the volume fraction, so the volume occupied by the aerosol, including any water taken up by the particles. So all of this is sent to RADAER in the radiation scheme. RADAER has some files that are pre-computed miscattering calculations, essentially, and combine those two things into aerosol optical properties, so absorption and scattering cross-sections and asymmetry parameters. Those have been averaged over the wavebands used by the model to represent the shortwave and longwave spectra. And then the radiation scheme uses those optical properties to compute relative fluxes and heating rates. So why use lookup tables? Well, the reason is that miscattering calculations are quite expensive, so it's difficult to do them at runtime. But the problem is that you may have seen that GLOMAP is a model that is able to simulate the size distribution of the aerosol interactively. That means that before you run the model, you don't know what the size distribution of the aerosol will be. So there's a dilemma here. It's too expensive to do it at runtime, but at the same time, I need to do it at runtime because I don't have the information before then. So here the solution essentially is I have lookup tables which essentially cover all the realistic combinations of mi parameter and complex refractive index. To simplify things, there are some assumptions. So the size distributions are assumed log normal, so that's essentially a bell curve in logarithmic space. And the width of the distribution is fixed, so that to save one dimension of the lookup table. So what do those lookup tables contain? Well, they contain our optical properties. So scattering cross-section, absorption cross-section, they are both given in per meter in the lookup tables, but normalized per unit volume of aerosol. They contain the asymmetry parameter, and they contain the volume fraction of the aerosol, which will be required in a moment for the next step. So this is how those lookup tables are defined. So there are different lookup tables for accumulation and coarse mode. The reason is that the range of size parameters covered by those two modes is quite different, so it makes sense to separate the lookup table so that we can put the resolution where it matters. And this is, well, it's really for your information, but this is the range covered by the different parameters. 51 values for most parameters, except for the imaginary part of the refractive index, which is now increased to 801 values because we didn't resolve low absorption well enough with 51 values. So, but the other two are fairly good. Where are those lookup tables set? So you may have explored rows already. So if you go in the UKCA name list in section 34, you will see those fairly barbaric looking names as I essentially describe what's the lookup tables being used. So you see that you've got lookup tables for the accumulation and coarse mode in the short wave and in the long wave. And this is where they are stored. So for most of you, it's just a black box, but next time you end up on that page and we wonder what those files are, this is exactly what they are. So they are lookup tables of aerosol optical properties for RADAER. So, how does RADAER do its job? Well, first it gets the wet diameter of the aerosol to compute the size parameter x. It depends on wavelength, so you need to loop on wavelength over the spectrum. Then you need to compute the refractive index of your mixture of aerosols. There are several ways to do this. RADAER does a simple volume-weighted average, including water as a component. So RADAER has a little library of refractive indices for different chemical species. So from left to right, that's sulfate, black carbon, organic carbon, secondary organic aerosol, sea salt aerosol, mineral dust, and ammonium nitrate aerosol. So once you have computed your size parameter and your ambient complex refractive index of your aerosol mixture, well, you exactly know which optical properties to get from the lookup tables, and you get those from the files. Then after that, there's a slight conversion of units because the Socrates radiation scheme doesn't expect scattering and absorption to be in per meter, but it expects them to be specific coefficients, so per unit mass. So you need just to do a little unit conversion accounting for density and volume of the aerosol. So more technically, where in the code are those things done? So there's two key functions. The first one is UKCA RADAER band average. So this is the key function that does most of the work in RADAER. So it takes the input from GLOMAP, computes the aerosol properties, and then average them over the wave bands that describe the shortwave and longwave spectrum in Socrates. So the integration is done at 6 wavelengths across each wave band. And it's weighted by a solar irradiance or the Planck blackbody function, depending on the spectrum, as mandated by the radiation scheme. Then there is another function which does something very similar, except that it doesn't do the integration of our wavebands. It just does the calculation at single wavelengths. And that's to obtain what's called the aerosol optical depth, which is a key diagnostic of RADAER that I will mention now. So aerosol optical depth is essentially a measure of integrated extinction over the column. It's an indirect proxy for the amount of aerosol weighted by the efficiency at interacting with radiation at that given wavelength. So RADAER gives an aerosol optical depth for each of the GLOMAP modes. So you get at the moment 4 aerosol optical depths. There are in section 2, which is long wave radiation. The reason why it's mostly technical is because long wave radiation is computed at all points, but short wave radiation is only computed on sunlit points. But we decided it made sense to have aerosol optical depth on all points. So they live in the long wave section. And AODs are 2D fields, so they are column integrated, but they have a third dimension, which is the wavelength. So in the unified model, having a third dimension, which is not the vertical, is called a pseudo level. And AOD diagnostics have 6 pseudo level, which represent wavelength of 0.38, 0.44, 0.55, 0.67, 0.87, and 1.02 microns. Those wavelengths have been chosen because they are favored by remote sensing retrievals of aerosol. So if you use Aeronet measurements, or if you use satellite retrievals from MODIS or Polder or MISER, they will be at those wavelengths, and the model gives you those wavelengths directly. Because you have more than one wavelength, you can also compute what's called the angstrom exponent. So that's a coefficient that describes the wavelength dependency of the aerosol optical depth. And that can also be useful to compare against satellite measurements, because the angstrom exponent depends strongly on the size. So it's a way to check that the model simulates the right aerosol size distributions. So this was the aerosol optical depth for extinction, so the sum of absorption and scattering. You can have it also for absorption only, so that's the absorption aerosol optical depth. Again, 1 per mode. So it used to require a branch, but I think now it is in standard. Yeah, it's been added for CMIP6. Same pseudo level, so same wavelengths as the AOD. And the good thing with the AOD is that it allows you to calculate the single scattering albedo, and I just noticed that this formula is wrong. It should read 1 minus AOD over AOD. Sorry about that. And the single scattering albedo essentially gives you the amount of scattering with respect to absorption. So a single scattering albedo of 1 means that your aerosol is purely scattering. That's the case for sulfate or sea salt aerosols. A single scattering albedo of 0 means that your aerosol is purely absorbing, which is never found in nature. But black carbon, for example, has a single scattering albedo of 0.2, so it's very strongly absorbing. There are ways to get single scattering albedos from remote sensing, so that's another way also to check that the model does the optical properties well. So there are other diagnostics available, and a lot of them are now standard, but before that they require branches. So you can have aerosol optical depths just in the stratosphere. For example, if you're interested in volcanic eruptions emitting aerosols into the stratosphere. Also, if you're interested in geoengineering, emitting aerosol directly into the stratosphere. And you also have vertical profiles of the aerosol scattering and absorption. So compared to aerosol optical depths, those diagnostics are not integrated over the vertical. And I believe that in the practical in the afternoon you will have a go at outputting those diagnostics and looking at what they give you. So I'm almost finished. Just mention evolution of the code. So the code is fairly mature and is not expected to evolve much in the future. It's perhaps a bit slower than we wish, and so we would like to make it a bit more performing. One idea is to choose better the integration wavelength across wavebands, so that for some wavebands we don't need 6 integration points. We could do the same with fewer integration points. The way that the refractive index of the aerosol mixture is computed is a simple volume average, and there are more sophisticated ways to do it. For example, what's called core shell approach, where you assume that you have a core made of, for example, black carbon, and then a shell of aerosol, which are condensated onto it. That would make a small change, probably not too radical, so it's not seen as a priority, but it may be done in the future to get the option of using core shell calculations. So in the previous talk, you had a mention of photolysis, and photolysis rate depends on sunlight, and the level of sunlight depends on aerosol scattering and extinction. This means that aerosols have an impact on photolysis rate. That impact has long been represented in a very simplified way in the unified model. But Michael Holloway has been working on linking RADAER to the photolysis rate calculations, and he's made good progress. There's now a branch that does that, and he may mention that tomorrow. So that's it really. just summary. So RADAER does aerosol radiation interactions in the unified model, and one of its main impacts, apart from having things like relative forcing of aerosols, is that you get aerosol optical depths out of it. So there's no paper just dedicated to RADAER, but you can find quite detailed description in the UMDP number 84, and also in that paper in 2013 in section 5 there's a description of RADAER. So that's the normal citation for RADAER. So I'm happy to take any questions. I will also be here for lunch if you have questions, and feel free to email me, of course. Thank you.